All right. So last time we talked about fatigue, a brief history, and why it's important. We highlighted the fact that it's responsible for an awful lot of money that's spent and an awful lot of failures. In fact, it's up to 90% or more of the failures in machines. We also talked about crack growth and that fatigue really is a crack growth phenomenon that causes materials to fail and even ductile materials to fail at stresses lower than their yield stresses or tensile stresses due to the fatigue phenomenon. We also said that there's three different phases of initiation, growth, and fracture. We talked about this last time from the microstructure view and how we get these cracks. All materials have cracks in them. The microstructure of the material matters, and we get these little cracks that initiate and start due to the material voids or dislocations or grain boundaries, etc. And then crack will start to form, and then it'll grow. It'll do elastic recovery. It'll have elastic recovery, which opens up the crack, and then it'll continue to grow in phase two, all the way until we get to where our stress intensity is equal to the fracture toughness of the material, and then we get unstable, sudden, and catastrophic failure. Okay, so Paris introduced a model that we can use to predict the change in the crack growth per the change in cycles. Okay, so we can look at dA and A here. That's the half width of the crack area from the last lecture, and then dN N is the number of cycles. So the relationship dA over dN is basically looking at the rate of change of crack growth as a function of the number of cycles, and it's given by this equation right here, where delta K is our difference in the stress intensity factor that we can calculate from that material. And we have this range here, K min and K max. And we saw last time that we can calculate K is equal to beta times the square root of pi times A. And we could look up the value for beta, and A is the half the crack width of that of that sample of the crack in that specimen, or the predicted crack, and then the sigma max minus sigma min. This is your alternating stresses that material that component experiences, and that's how we get our delta K. Okay, when we have a delta K that's less than the theoretical change in the stress intensity factor, it's kind of like being below that fatigue limit. Okay, so that's over here in this range. Okay, so we don't get these the cracks don't start to grow until our stress intensity factor gets above this threshold, and then finally gets to our fracture toughness of the material. Okay, so this is the Paris law, okay, for crack growth and fatigue, and it's just a complementary way of looking at that fatigue phenomenon. Now the parameter in the Paris equation can be found from this table, A and N, for these different types of materials. And if we integrate the Paris equation, which was done by Barsom, you can actually solve for the number of cycles based upon a final crack size and an initial crack size, the beta for that geometry condition, and then the parameters A and N, which come from this table down here, and it's given in both SI units and US units. Okay, so the Paris law can allow us to get an estimate of how many cycles it's going to take for a crack of this size to get to this size, and then it's just plug and chug. Make sure you get your units right, and you can estimate the number of cycles for a crack to grow from the initial size to final size. So just like we saw with the introductory lecture to the SN curves or the Wöhler diagram, we see that the mean stress dramatically reduces the fatigue life, and that means if we have this cyclical stress and we have some non-zero mean stress that's tensile, we said also, compressive stresses help, but if we have a tensile mean stress here, then it reduces the fatigue life significantly. And these are just plots of the Paris equation for crack growth for different stress ratios, okay, where the min and max stress is plotted here. So if we have a fully reversed stress, this is our nominal case here. So if we follow this line all the way down, then we see it takes a higher stress for cracks to initiate and propagate. If we have a mean stress that's present, then we can see how these drop down. And then if you follow this one down, which has a amplitude stress ratio of 0.8, that the cracks will initiate at a much lower stress. So when you design a machine, okay, that you expect to have dynamic loads, you must keep in mind that you do not, in general, want to introduce tensile loads, if possible, as a design philosophy. Now, there's all sorts of caveats, and you can only kind of follow your learn by doing, but in general, you want to minimize the residual tensile stresses in machines, okay, because it'll cause cracks to initiate at a lower amplitude. Okay, now what we would really like to get to is where we would really like to get to is being able to estimate fatigue failure. Okay, but the best information that we have about fatigue life of a component comes from the actual tests of that component in a service environment. That's often not realistic, and we don't necessarily have, like 40 days to run all the cycles or a year or whatever. So in the absence of tests, what we can do is use the material information, the manufacturing process, published data, and then use this data with some correction factors for our particular application. Okay, so the way we do that is we can find down here, you'll see we have the endurance limit for materials with an endurance limit, or the fatigue life for materials that have a fatigue life, and these are stress values. And then what we can do is modify them based upon the load, size, surface, temperature, and reliability that we want. And all these C factors are serve to make our estimated endurance limit more conservative by considering these factors. Okay. So what we can do then is take the published values for the endurance limit or fatigue strength and then correct them for our application. So what we're going to do is we'll just talk about how each one of these factors are introduced and when we need to use them and their effect. Okay, and the reason we have this different notation here, this SE and SF, it's like this is your endurance limit and this is your fatigue life. This is taken for materials that don't have that sharp endurance limit line, and this fatigue life here, fatigue strength of the material, is for materials that have been run to a certain number of samples, typically 5 times 10 to the 8 for aluminum. Okay. So when we take a look at this, we need to come up with our starting point, our first point. So that's we're going to find SE and SF in this equation. And the way that we do that is we take, we can look at the different fatigue ratios and use the crude relationships to find between the ultimate tensile strength and the fatigue life for that material. Okay, so we talked about this last time, and based on the test data, we found that for most steels that have an endurance limit, we can use 50% of the ultimate tensile strength as the endurance limit. And if you kind of look over here at this data, this shows the failure lines when you use that. And as you can see, if some of them are below and some of them are above, there's not a perfect fitting of the data. So it's a very thing to keep in mind. Okay, so we're starting with fatigue life that has an awful lot of scatter in the actual failure data. Okay, so we certainly want to modify that so we're more conservative for our particular application. I cannot stress that point enough. Okay, this data has a lot of spread, so we can start here at a fatigue life, and if we use the fatigue strength based upon the tensile strength just by multiplying it by 0.5, for example, you see that the failure points occur both above and below that line. Okay, and same thing for irons and aluminums and copper alloys, and you can see them right here. And so we use a little bit different ratios for them to try to fit the data and appropriately. For aluminums, we use 0.4. For irons, we use 0.4. And those are for irons that have an ultimate tensile strength of less than 60 kpsi. For those that have a tensile strength of over 60 kpsi, we use a fixed value of 24 kpsi. We do the same thing for steels, 100 kpsi for those that are greater than 200 kpsi. For aluminums, we fix it at 19 kpsi. For those with tensile strengths that are greater than 48 kpsi. And for copper, we fix it at 14 kpsi for those copper alloys that have tensile strengths that are greater than 40 kpsi. So pause here if you don't understand what I just said, and make sure you understand it. What we're trying to do again is go back here and find our starting points for our endurance limit and fatigue strength for different materials. So these are pretty commonly used materials, obviously steels and aluminums for most engineered products. And these are our starting points for the fatigue life. So then we can plug them in as the starting point into this equation. Okay. All right. So we have to correct the fatigue life now that we found, either from looking at the published data or just using an ultimate tensile strength to get that initial estimate for the fatigue life. Then we can modify it based upon the loading, size, surface, temperature, reliability, and environment factors. Okay. So the correction factors always make the fatigue strength or endurance limits smaller. So each one of these is less than 1. Okay. If we look down here at the difference, again, just showing these SN diagrams for steel and aluminum. We're picking those values that are about 50% here. That's this value for the endurance limit. And then we're going to modify that with the fatigue factors. Now for aluminum, we go to a certain number of cycles, which is usually 5 times 10 to the 8 cycles. Okay. Now the material matters, and so we need to make sure that we understand how that material is made. Like if you have a wrought alloy or die cast or sand cast alloy, they have different strengths. Okay. So any cast alloy typically is going to have a lower fatigue life than a wrought alloy. Okay. And again, there's no need in steel, as in steel for aluminums. Okay, so there's no endurance limit, so we use that 5 times 10 to the 8. All right. So since most of the published data is for that rotating bending test, that RR-Moore test, where you have this nice axial shaft where you have 0 shear and you only have those bending stresses that are reversed that we talked about last time, we just can use a load factor if we are just in bending stresses of 1. However, as we saw last time, axial loading reduces the life and can reduce it by up to 30%. So we can use a load factor of 70. So you might ask, well, what do you do if you have torsional loading? And so we will, for torsional loading, we just leave it as 1, the same as in bending. However, we deal with the torsional load by calculating the effective von Mises stress for that use case where we have that shear stress, and then we can use that. Okay, and that gives us sufficient confidence in the data. We can use a load factor as 1. So that covers bending, axial loading, and torsion. Okay. So rotating bending tests use that 0.3 inch rotating round beam. If the diameter of what we're trying to estimate the fatigue life is larger, then what we do is we can modify it with a size factor. Okay. And this is the coefficient, the factor that we use. If the diameter is less than 0.3, that's where we got most of the test data for the fatigue life. Then we just say the size factor is 1. 0.3 inches is about 8 millimeters. So if we say, well, if we're between 8 millimeters and 250 millimeters, we can use this equation here, where D is the diameter of that shaft that's in rotating bending, or that shaft that's with that load condition. We can use that diameter here. If the diameter is between 0.3 inches and 10 inches, it's the same. We can use this. So this is for if you have your dimensions are in inches, you can use this equation for larger shafts. If your dimensions are in millimeters, you can use this equation. Okay, so don't make the mistake of using this equation when you have metric units. Okay, we can also get a size factor for different shapes by using an effective equivalent diameter based upon the 95% of the area. Okay. So for different shapes, we can use this A95 equation and find the equivalent diameter based upon this 95% area. And this has been calculated for us for different geometries. Okay. So the equivalent diameter then becomes your A95 over this value here. And this is some common shapes where we can calculate that A95 area if we have rotating solid or hollow round shaft, or if we have a non-rotating shaft here, we can use this. Okay, but it's subject to the cyclical loading. And then these are some other shapes if they're subjected to the cyclical loading that we can use their A95 area as well. And then we can plug that in and get our equivalent diameter, and then put it in to these equations here. All right. The next factor that we have to consider is the surface effect. So the rotating beam tests, those are done with polished surfaces. Okay. But obviously we can't polish every surface, because a mere polished surface is really expensive to produce. Most engineering machine components are not polished. So they have rougher surfaces, and those rougher surfaces result in a lower fatigue life. And water, the presence of water, also reduces the life of some materials. So this is one of the graphs from the book that just shows the difference of different manufacturing methods. And so what we can do is look up the ultimate tensile strength of that material, and then look at how it was manufactured, if it was forged, hot rolled, or machined. Then we can go up and then find the appropriate intersection with that material, come over here and get our correction factor, and then use that in our fatigue life. Okay. This is another way of getting that surface factor, okay, from surface roughness. So if you know the RA, surface roughness, which you can get from a profilometer, or maybe even just looking at a optical comparison gauge. If you have your surface roughness, you can look at this graph over here. So again, you take your ultimate tensile strength, and then you'd go up and find that surface roughness, and then come over here and get your surface factor. If you don't have the surface finish, you can use this equation here as an estimate to get that. All right. And if you come up with a value that's greater than 1, then you just set it to 1, because we're not going to increase the fatigue life of it with these factors. Okay. So if you have ultimate tensile strengths in SI units, you can use A's and B's for these different manufacturing processes. If you have them in SI, if you have them in English units, you can use these factors here. Okay. So the reason that we're putting these graphs in here in this one place, so you could really take this slide deck and just go through it and pick all your factors. All right. Now you might tell yourself, oh, well, why don't I just plate my material with some coating and make it harder and make the nice, shiny, smooth surface, and then I'll increase my fatigue life. Well, that's sounds good, but it doesn't work in practice. In fact, that plating can actually introduce residual tensile stresses and reduce the fatigue life, okay? Because you're adding material at the top, and it's separate, can put the surface in tension. And this is just an example of what might happen to your fatigue life. If you have an unplated sample and then you plate it, you can see how it drops that fatigue life. Okay, so these are some coatings. Okay, this is a nickel plated specimen for steel. It's nickel plated and then peened, and peening is where we shoot small pieces of material at the metal to introduce compressive stresses. It is one of the best processes that you can use to increase fatigue life, and many components are peened. Many gear components are peened. Many aircraft components are peened to introduce those residual surface stresses. And we'll talk a little bit more about that later. If it's unplated and unpeened, you see we have a lower life. If it's peened and then plated, we actually have a lower life than if we had an unplated, unpeened sample. Okay, which is pretty interesting. If it's plated and unpeened, we have an even worse life. Okay, so, you know, as a designer, you have to keep in mind, if you need to plate something, you're going to change its fatigue life, and you need to understand and kind of do the work to really analyze your design and make sure that you're paying attention to these things. Okay. The next factor that we have to consider, this is our third of 5, is or fourth of 5 factors. We usually take the fatigue test data, or the test data that we have available is usually from room temperature data. Fracture toughness decreases at lower temperatures, but increases at higher temperatures, which could help us. The endurance limit in steels, though, disappears at higher temperatures. Okay. Temperatures above 50% of the melting temp makes creep a significant issue, and that's where you have, if you have 50% of the melting temp, you have a constant load, then that material will elongate due to creep, and you can have a failure because of that at stresses well below the tensile stresses strengths of those materials. Okay, our yield strength decreases with increasing temperatures. Okay, and so what we have to do is, if we have a material that's in service at elevated temperatures above 450 degrees Celsius or about 840 degrees Fahrenheit, we can use these equations for steel. Okay, if you have elevated surface temperatures for other materials, you'll have to go and look those up in handbooks and guides and standards. Okay, so for steel, though, if we have these temperature ranges, we can use this temperature factor to correct for them. Okay, now the last one we look at is the reliability. Okay, and as you saw at the beginning of this lecture, a lot of the materials have a pretty wide spread in where they actually fail around there. And so what we can do is say, well, we really want to have a higher reliability. Okay, so if you use those published data, then you're going to have about a 50% reliability. Okay, so that's unacceptable for most designs. So to increase your confidence, We can correct the endurance limit or the fatigue life by the following correction factors. Steel usually remains within about 8% of its mean failure value. Okay, so if we say that our standard deviation is about 0.8% of the mean, and this is what the case with steel, if we want a 50% reliability, we can just set our reliability factor to 1. If we have to have a higher reliability, then we can use these factors. So if we want to have a 95% reliability, for example, or 99%, okay, we have to reduce the fatigue strength of that material by about 20% by multiplying it with this reliability factor of 0.8. Okay. There's some other effects we have to consider. So the effect of fresh water on steel, okay, can actually reduce the fatigue life. If we actually have it in a corrosive environment, we get corrosive fatigue, which we mentioned in the last lecture, and that dramatically reduces the fatigue life. If we look at in this case, we're looking at the alternating stress that it can endure. So the amount of alternating stress that can be endured drops dramatically if we have the presence of water or a corrosive environment. Okay, if we look at instead of the alternating stress value to failure, or the fatigue limit as a function of its tensile strength in different environments, then we can see that for air, we have this relationship here. For chromium steels and fresh water, we have this relationship, and then for carbon and low alloy steels, we have this relationship here. So what we can say then is that if we have carbon or low alloy steels in fresh water, we can use an endurance limit of about 15 kpsi, okay, for the fatigue strength. Okay, that puts us right here. There's also some tests that have been done for aluminum. If we have a zero mean stress and we have an alternating stress, and we look at aluminum in air or aluminum in salt water, we see that the effect of that corrosive environment dramatically drops the amount of alternating stress that can be endured for that life. Okay, I've heard it said that people believe that the reason that some of these aircrafts fall into the ocean that are old and aged is probably from some form of fatigue failure that really just couldn't be measured. So you hear about some aircrafts that just fall out of the sky for no reason. It's probably due to fatigue. So if I were you, I would not get on an old aircraft for that reason. All right. So now with this information, we can plug in our 5 correction factors and correctly compute the endurance limit that is corrected for loading, size, surface, and temperature effects, and as well as reliability. Okay, so again, we would do is start here with our endurance limit based upon the material. We can plug that in and then go through the load, size, surface, temperature, and reliability. The load has to do with whether we're in bending or tension or torsion. The size has to do with the diameter or the effective area. The surface has to do with the surface roughness and its manufacturing process. And then the temperature has to do if we're in elevated temperatures. And then we have a nominal 50% reliability if we just leave the reliability as 1. If we want to reduce that for steels by to get a 95 or 99% reliability, we have to make this reliability factor about 0.8. Then we can finally get our endurance limit for that material or our fatigue strength for that material. Okay, and these are just a copy and paste of those values. Okay, all right. So now what do we do? How do we draw these SN diagrams and then find out where we are in those diagrams? Okay, so the correction factors that we just went over, those are for high cycle fatigue. Okay, so we're trying to find out, okay, if we're way out here like what's our endurance limit, or can we go all the way out here for our fatigue strength for materials without that knee here. Okay, so if we want to investigate what we would call low cycle fatigue, this region from 10 to the 3 to 10 to the 6, then what do? Okay, so what we'll do is we can start with SM, which is the fatigue strength at 10 to the 3 cycles. We don't use correction factors for SM, but we use the corrected value here for the SE and SF based upon what we just did with our correction factors. Okay, so if we have bending, we make SM as 0.9 times the ultimate tensile strength. If we have axial loading, we say SM is 75% of the ultimate tensile strength, and we can plot that first point, and then we have that second point from our corrected fatigue analysis that we just did. And then if we want to find the failure line from SM to SE, okay, SM to SE, we can just plot that based upon those relationships. Okay, so this is for a material that has an endurance limit. Okay, we can just take that log-log relationship and plot the line from those points here. If we have a material that has no knee, we can use these equations here to find the expression for that line for a material with no knee. Okay, to find the N2 at 5 times 10 to the 8. All right, these are the factors that we can use for those equations. For if we want an N2 that's a million cycles, we use Z of -3. If we want it at 5 times 10 to the 8, here, then we use a Z of minus 5.699. That's what is used right here to find that second point in the graph. Okay. All right. All right, so this is an example. This is just for some bar, and I'm just going to talk you through the process. This is the example in the book. You can also walk through this slide in more detail yourself. Okay, but again, we start off, we want to find our fatigue life. And in this case, it says, create an SN diagram for a steel bar. How many cycles of life can be expected if the alternating stress is 100 megapascals? SUT has been tested at 600 megapascals. It's 150 millimeter square bar, has a hot rolled finish. The operating temperature is 500 degrees C, which is over that 450. And the loading will be fully reversed bending. Okay, we want an infinite life, and we want a reliability of 99.9%. Okay, so the first thing we do is, this is steel. Okay, and let me make sure where it says it's steel. For ferrous material. Okay, so then we can use 50% of its ultimate tensile strength, which we're told is 600 megapascals. So then we start off here with the SE, and then we have to correct it. Okay, so the loading is bending, so we just put the loading to 1. We have this different cross-sectional area, so we calculate the A95 area based upon those equations for the A95 area to calculate an effective diameter. And then we use this diameter in the size equation because we look at the range, and then plug those values in and see that we are reducing that fatigue life because of this size factor here automatically by 75%. Okay. Then we go to the surface factor. In this case, we can use the data in that table for a hot rolled finish. We just can get the A and B values from that table and then plug in 600 for SUT and find out that our surface factor is about 60% now. So we reduced it by 75%, now reduced it again by 60%. And then we want the reliability to be 99.9%. So then we multiply, we go to the table, and we see that we have to multiply the fatigue life by 75%, about 75%, to get that 99.9% reliability. And then we can just plug them all in together. Okay. And once we do that, where's the temperature effect? So we're missing one here. This is 4. and this is 6, so I think I actually cut it off. Sorry about that. But for the temperature effect, what is done is we use this equation. They said it's 500. So this equation is used right here, and this T is set to 500. When you do that, you're going to get the value here for temperature of 0.71. Okay, so we started off with an endurance limit of 300 megapascals. Then we corrected for all these things, load, size, surface, temperature, and reliability, and ended up with an endurance limit of 70 megapascals. Now, we have a problem because how many cycles of life can be expected if the alternating stress is 100 megapascals? Okay, so infinite life is required, but we're not going to get infinite life here because we already can see that we are below the endurance limit is below the service load. Okay, so we can then go and create our SN diagram and see how long is it actually going to last. Okay, so we can start off with that SM data that's at that 10 to the 3 cycles, and we say it's 90% of SUT. Okay, that's what we're doing right here. We're just creating this low cycle fatigue because we know we're not out here. And then we can find the expressions for those lines and calculate the B from the 1/3 log of SM over SE. And we just calculated SE, so we can find B. And then we can solve for A by plugging the values for SM and B in. We get A is equal to this, and then we can plug A into our equation here and get an expression for N from 10 to the 3 to 10 to the 6. So that's that line there right here that we'll get for that life. Okay. So the number of cycles of life for any alternating stress level can be found from these equations. Okay. So if we want 100 megapascals, we can plug that in and then solve for the number of cycles that gives us that 100 megapascals. Okay, so we put 100 in, take the log of both sides, and then solve for N. We solve for N, we get 3 times 10 to the 5 cycles. Okay, and this is less than what we wanted, so we don't actually have infinite life. So we'd have to change the design of this to increase that life. Okay, this is what it looks like. That's SUT, and we come down here, 90% of SUT for this 10 to the 3 cycles. We have our endurance limits here, and then we find this line from those expressions, and then we can look at where that alternating stress that's experienced for the sample intersects that line, and that's our failure point, and we can calculate all this stuff. That's what we did in that example. Okay, so now what is the corrected fatigue, the estimated SN diagrams for non-ferrous material? That's a 1.5 inch round aluminum bar, a 99% reliability, and we want the fatigue at 5 times 10 to the 8 cycles. This is 6061 T6 aluminum. SUT is 45 kpsi. It's a forged bar. That's 1.5 inch round. Max operating temperature is 300 degrees Fahrenheit, and it's in fully reversed torsion. Okay, so we start off with the same process. We can get our fatigue life, which is 40% of the ultimate tensile strength for materials that have less than 48 ksi. So in this case, then that puts us at 18,000 psi, and that's the value for 5 times 10 to the 8 cycles. Okay, there's no knee in aluminum, so this is how we deal with a non-ferrous material. The loading, we're told, is in pure torsion, and the load factor is 1, and that's because we're going to use the torsional stress. We're going to convert it to an equivalent von Mises stress, and that accounts for that, even though it is the test data is for reversed bending. When we're in pure torsion, all we have to do is make sure that we take that torsional stress and and convert it to the equivalent von Mises stress, and then that covers that. Okay. So then we got to find our part size, because this is larger than the 0.3 inches. For the test specimen, we use our equivalent diameter, which in this case is round, so it's 1.5 inches. And we can calculate our size factor. We can then find our surface factor. We can look at the data. It's forged. Okay, so we plug the values in for forged finish. Those relationships were developed for steels and may be less accurate for aluminum. Okay, so that's a caveat that we have to remember. But we're still using it to reduce the life by 90% or 10%. The temp is below the equation that we have, and that equation is given for steels. So we'll assume that the temperature factor is 1. Then we can take the reliability factor for 99% of 0.814. And then plug those values in to get a corrected fatigue strength. And that's, again, at not the endurance limit, but it's at 5 times 10 to the 8. So then we plug all those values in, and then at the end we get a fatigue strength, a corrected fatigue strength for that material. That's about 11,000 psi. Okay, so then we want to create the SN diagram. So in this case, we start off with 90% of point of SUT, and then calculate the coefficients that we need for the line, plug those coefficients into the line, and then we're told here we want the fatigue strength at 2 to the 7 cycles, so we can plug in 2 to the 7 cycles here and find the fatigue strength that we would have, and we find that as 15,209 psi. In this case, this fatigue strength is larger than the fatigue strength because it's a shorter life. Okay, so we calculated the corrected fatigue strength at 11,000, but because we don't need it at 5 times 10 to the 8, we actually need it at 2 times 10 to the 7. Then we plug those in, we get a little bit, we're allowed to get by with a higher load because we have less cycles. Okay, so down here, it says, notice the order of operations. First thing we need to do is get the corrected fatigue strength using those correction factors. Only then can you make the SN line, okay, that passes through that corrected value. Okay, if you did that first, though, you'd get the wrong numbers, and if you calculated those values and then applied the correction factors, you'd get an incorrect results. Okay, these are exponential functions, so superposition doesn't help. Okay, so you have to do the correction first, so make sure you get that order correct. All right, so we'll stop here with this lecture, and then next time what we'll do is we'll talk about how do we look at the stress concentrations and how are they affected by dynamic loads.